So in this section we'll talk about heat transfer. Three mechanisms. So heat is energy in motion, and so there are three ways we usually count that heat is transferred. And so you should pause this and see if you can think of what those are. The first one is called conduction, which is transfer by direct contact. Right, and so that's, cold next to an object that's hot, and the heat flows in this direction just by contact. The next one is convection. Convection is really the transfer of heat by moving matter. So here, the matter isn't moving, it's just that the heat is getting transferred, right? Really, it's just kinetic energy is being transferred to molecules adjacent to each other, and the heat kind of moves along. In convection, heat's transferred by moving matter. So we've all seen, for example, a fire or something like that, right? And so if you look at a fire, that's supposed to be a fire, right? You can see warm air kind of rising above the fire, right? This is convection. Heat gets carried away with the wire, heat gets carried away with the warm air. So what really happens here, you should ask, why does this stuff rise? All right, see if you can answer that question without waiting for my answer or without listening to my answer. What happens here is that the fire warms the air. Warm air expands, and then that expanded air is less dense than the air around it, and so it rises through it. And so that's how this is sometimes called natural convection. Air conditioning systems use forced convection. That is to say, warm air or cold air, depending on whether it's summer or winter, is pushed through your duct system in your home, and in July, cool air is pushed into your house. That's forced convection. That's cold air being pushed around. In that process, of course, warm air is somehow moving out. So, for example, air conditioning systems use forced convection. That's, you have a fan that's moving air by force, right? And so those are two types of convection. Natural convection, which just happens because of the physics of the situation, with no sort of intervention, other than maybe starting a fire. And then forced convection, where you're using a motor somehow to move mass from here to there. Finally, the third example of heat transfer is heat transfer by radiation. And so heat transfer by radiation is just basically light. Electromagnetic waves carry energy, and so they can move thermal energy from one place to another, or energy in light form, say, converted to heat when it's absorbed by another object. And so we'll talk about the three of those. Conduction and radiation have sort of fairly straightforward, well, fairly easily defined equations that represent how they the physics. Convection, not so much. So I'll just talk a little bit about convection. We'll spend a little more time on conduction and radiation because the mathematics of them is a little more easy to express. So this section is on heat transfer by conduction, and so we're going to think of it this way. We have some object here which is at temperature T hot, and then we've got a material here, and then we've got another object over here that's at temperature T cold. And it doesn't matter too much what these materials are. What we're going to talk about is how the heat transfers through this material, right? And so this is this could be like the inside of your freezer, the inside of your freezer and the outside of your freezer, or this could be, the inside of an ice chest, the inside of an ice chest and the outside of the ice chest, or the inside of an ice chest keeping things hot and the outside of an ice chest. And this would be the material in between. And so this is going to be some distance d, right? If I were to draw this in 3D, like this, then there would be a contact area here, and that's important, the contact area here, because how much area is allowed for the object to be in contact determines how well the heat flows. And so it turns out that the power, that is, say, power is energy per time, right? In this case, we would call it, we might call it the change in heat over the change in time. Sometimes that's just written as Q over T, right? That's the heat that's flowing this way, the Q, the energy leaving this guy and going into this guy. I should draw him 3D also, maybe, if we're going to do that, right? And so this is the power, the energy per time that's transferred across here. And so it turns out the power depends on one, the temperature change, which is T hot minus T cold. And you should be able to sort of understand that fairly easily. The greater the temperature difference between the inside and the outside, the faster the heat's going to flow. If they're at the same temperature, no heat's going to flow, right? If this one's hotter, the heat's going to flow that way. If this one's hotter, the heat's going to flow that way. The bigger the difference, the faster the heat flows. And so the second thing it depends on is the area. The area of the material carrying key. We're assuming it's a uniform area, right? But it's obviously, if there's just a tiny area of contact for the heat to move, then not much heat is going to transfer, right? The bigger the contact area, if you touch your finger to something that's really cold, not much heat is going to transfer. If you touch your whole hand to it, more heat is going to transfer, right? From your hand to the cold object. So the area matters. That's the area. D is how far the heat has to travel. The farther it has to go, the slower the rate of heat transfer. If I have two things that are almost right up against each other, the temperature difference is over a very short space, heat will flow faster, right? So finally, the last term is the thermal conductivity K of the material that's doing the heat transferring. So if this is styrofoam, you would get styrofoam has a very low thermal conductivity, but if it was copper has a high thermal conductivity, and so the heat would transfer faster with copper than it would for styrofoam. And so if we put all this together and sort of figure out, I'll just do it up here, right? It turns out that the power is equal to, so the greater the thermal conductivity, the faster the flow, and so the K goes here. The greater the temperature difference, the faster the flow, and so that's T hot minus T cold. And finally, the greater area, the faster the heat flow, and then the greater the distance, the smaller the heat flow, the lower the heat flow. And so that's it. It's usually written this way: P equals K A delta T over D, something like that. It's the rate of heat flow by conduction. I kind of made that. That's not this guy. And so I'll write down a few Ks for different materials, and then we'll do an example. So we'll do a few substances here. Here's diamond. It's 2,000. Again, this is the thermal conductivity. In watts per meter degree Celsius. And so that's 2,000 for diamond. For copper, just a few common materials, it's 390. For steel or iron, it's 80. There are lots of flavors of steel, so you might see a problem with the different with steel for a different number. Ice. Steel obviously isn't an element, and so it can have different amounts of carbon or iron or stuff like that in it. Ice is 2.2. Glass is 0.84. This also, this would be concrete also, turns out. Water, 0.6. Fatty tissue is 0.2. That's the stuff that's around your body that kind of insulates you from the outside. It's got a low thermal conductivity to keep you mostly warm. Wood, 0.08 to 0.16, somewhere in there. Snow. This is why animals bury themselves in the snow in the wintertime, because it's got a very low thermal conductivity. Air, 0.023. Styrofoam, if we can still get on the screen, is 0.01. This is what your insulated container has stored in it sometimes. So you can see that if you want to insulate something, you want to grab things down here, right? If you want a high thermal conduction, you want to grab things up here. So the question is, a styrofoam container, this would be like an igloo, an ice chest, has an area of 0.950 square meters and a wall thickness of 2.5 centimeters. So it's, it's a box. I don't know if I can draw this. Right, but it's got a thickness to it, and so it has a, I don't know how to draw that, but you get the idea, right? It's kind of a, so here's the outside of the box, here's the inside of the box. I guess the average of those two is 0.95 meters. The wall thickness, so this distance here is 0.025 meters. And what we're going to do is fill it with ice at 0 degrees C and figure out how much will melt in a day, assuming that it stays at 0 degrees inside, right? And so this is asking actually for, a mass of ice is what they're asking us for. And we're going to have to get that somehow from the stuff we've been talking about, right? The formula we have is the power is equal to Ka times T hot minus T cold. So a styrofoam container, this is like an ice chest, has an area of 0.95 square meters and a wall thickness of 2.5 centimeters or 0.025 meters. If it is filled with ice at 0 degrees C, how much ice will melt in a day if it has to stay at 0 degrees Celsius? Assume we're going to assume the outside temperature is 35 degrees Celsius, and that of course means this is T cold. And what we're really after is how much ice will melt, and so we're looking for a mass. And this is weird because we haven't really talked about this in terms of this section we've been talking about on power, right? What we have for power, this is a heat conduction problem, right, is power is equal to Ka times T hot minus T cold over the distance, right? And so it turns out we can calculate this because we know that that it's styrofoam, and so we just saw that the styrofoam has a thermal conductivity of 0.010 watts per meter degree C. We know what the area is. They told us it's 0.95 square meters. We know what T hot is. We know what T cold is. And this distance is this guy. D is equal to 0.025 meters. And so the question is, how are we going to do something with this to get a mass, right? And the answer is power is equal to Q over time, right? And so the time that's going to be involved, we can rearrange it and say Q is equal to power times time, where the time is 1 day and the power is this thing. And if you remember, so this is the amount of heat that's going to move into the ice chest from the outside over 1 day if the outside is at 35 degrees C and the inside is at 0 degrees C. And if you remember from the section we did on heat of fusion, Q is equal to M L sub F. This is going to determine how much ice this much heat will melt. And so M is equal to Q over L sub F, right? But Q is power times time, and so the mass is equal to the power times the time over the latent heat of fusion of the ice. And so that comes out to be M is equal to, so all of this, it's Ka T hot minus T cold. Let's just calculate that first, right? I'm just going to calculate P first. So P is equal to Ka T hot minus T cold over the distance, which is 0.01 watts per meter degree C times 0.95 meters squared times T hot, which is 35 degrees C minus 0 degrees C over 0.025 meters. And what I get for that is about 13.3 watts. All right, you should be able to cancel out all the units. Meters cancels with meters squared and leaves meters. That cancels with this. Meters degrees C cancels with that. And if you multiply all that stuff out, you get 13.3 watts. So this number is telling you the rate at which energy is leaving. And we can use that in this equation to determine the amount of mass, right? And so I'm just going to clear off a little spot up here and say, look, the mass is equal to the power times the time over the latent heat of fusion, which is 13.3 watts. Now the time is 1 day, and we need it in SI units, and so you can check that, but it's 86,400 seconds, right? We've got to have the units consistent. And then the latent heat of fusion is 3.34 times 10 to the fifth joules per kilogram. I'm just going to have to clear off a little more room here. And so I'll write this as the top. This becomes 1.15 times 10 to the 6th joules over 3.34 times 10 to the 5th joules per kilogram. And what I get for that is about 3.44 kilograms. And so if you fill an ice chest with ice at 0 degrees C and keep the inside at 0 and the outside at, well, the inside should stay at 0. Yeah, if the outside is 35 degrees Celsius, which is maybe 95 degrees Fahrenheit or something like that, 3.44 kilograms of that ice will melt in a 24-hour period. So I've already mentioned a few things about heat transfer by convection. You can have warm air rising over fire. So here's my fire, and here's my warm air, and I'm moving heat upward by moving the warm air. The heat is moving rather than transferring by thermal contact and flowing from one object into the next. The mass that's hot is just carried along, and so the heat moves that way. This would be fire. An example of this is what's called a sea breeze. And here's the idea. I have over here, I have a beach. Uh-oh. That was not going to be very good. And here's some water, say. So say this is the ocean. And up here, I know it's red, but pretend it's not. I have the sun. And so what happens, if you've been to the beach, you've probably noticed this. When the sun is shining on the beach heats up faster than the water. And so the sand on a beach is much hotter when the sun is shining than the water is. And so you have cool air here and hot air here. And what happens as a result of that is this air rises upward. Right? And because it's warm, it gets heated, it expands, and it's lighter, and so it rises. And so it has to get replaced, and so the cool air comes in this way. And this air has to get replaced, and you end up with a cycle like this. But if you're standing here on a hot day, you get what's called a sea breeze in the daytime. The cool air will be coming in off the water, and what it's doing is it's replacing the hot air that was lifted off the beach because it was expanded and had a lower density. At night, so this is daytime. At night, it turns out the opposite happens. So if I redraw this diagram here, at night, I'll just be silly and put a little moon up there, right? So here's the nighttime, right? Here's my beach. Now it turns out, because the sand radiates so well, we'll talk about that in the next chapter. Now this is cold, and this is warmer. The water maintains roughly a constant temperature between day and night, but the sand gets real cold at night, or much cooler at night, and much hotter in the daytime. So now you have the opposite effect. Now the air is rising from this side, because this air is being heated a little bit, and it does this. And so now the breeze goes in the opposite direction. So that's an example of convection. So the last one we'll talk about is heat transfer by radiation, and this deals with the Stefan Boltzmann law. The Stefan Boltzmann law of radiation says that the power radiated by an object at temperature T is sigma A epsilon T to the fourth power. And so sigma is 5.67 times 10 to the minus 8th joules per second meter squared Kelvin to the fourth. Or you can sometimes write it as 5.67. You can combine the joules per second to watts times 10 to the minus 8th watts per meter squared Kelvin to the fourth. It's just a constant, like the gravitational constant G and so on. A equals the exposed area. E is the emissivity. And finally, T is the temperature in Kelvin. So E is just a measure of how well something radiates. It turns out things radiate and absorb radiation according to the same constant. And so a very efficient thermal radiator will have an emissivity of 1. Something that doesn't absorb or emit very well will have an emissivity closer to 0, and so, or they can be anywhere in between. Most of the time we'll just be using 1 for this number. And so if you look at this equation, the striking thing about this equation, it shouldn't be too surprising that there's some property of the material that tells how well it radiates. It shouldn't surprise you that the exposed area determines how much radiated power there is. If you have a whole bunch of logs on a fire, it's going to radiate more power than if you just got one log burning on a fire, even though they're all at the same temperature. Right? Logs roughly burn at the same temperature. What's surprising here is that the radiated power goes as the fourth power of the temperature. And so if you have something that's twice the temperature of another thing, in Kelvin, by the way, so that would be a fairly significant temperature difference, right? It would be 6 times, it would radiate at 6 times the power. This starts to show up in things like stars, where you actually can have stars that are twice as hot as other stars, or 4 times or 10 times as hot. A star that's 10 times as hot will burn up its fuel 10,000 times faster. And so you could have a star that'll live 10 billion years, like our sun, but a star that's 10 times hotter will only live 1 million years. So 10 billion versus 1 million, that's what a factor of 10 in the temperature will do. And so it produces a factor of 10,000 there. So let's do an example or two with this. So one more quick thing before we do examples. Objects both radiate and absorb radiation. That is to say, my hand here is emitting radiation according to this formula, according to the Stefan Boltzmann law. But it's also absorbing radiation from objects around it. They're emitting heat and it's hitting my hand and it's being absorbed. The factor that I absorb is the piece that I absorb is this piece, where that's the temperature of the surroundings. The area is the area of my hand, because I can't absorb off a bigger area than my hand. And then this is how much I radiate. And so if my surroundings are hotter than me, then my net is going to be positive. If I am hotter than my surroundings, then my net is going to be negative. That's to say I'll be losing power rather than gaining power. And so, again, T2 is the temperature of surroundings, T1 is the temperature of the object. You can write it just as this way. You can factor out the sigma epsilon E, because it's always the thermal properties of my hand, and then you can just put T2 to the fourth, which is the surroundings, minus T1 to the fourth. If it comes out negative, that means you're losing heat. If it comes out positive, that means you're gaining heat. And so let's talk about So in this problem, we'll say, what is the heat transfer to an unclothed person of skin temperature 33 degrees Celsius in a room at 22 degrees C if the emissivity is 0.97 and the area of the person is 1.5. And so here's my formula. T2 is the temperature of my surroundings, and so that's 22 degrees C, which is 295 Kelvin. It's really important that you get the Kelvin in here. These only work for Kelvin, and so you'll see problems where the temperatures are in Celsius, and you'll have to correct that. And so this is 33 degrees C, which is 306 Kelvin, right? Let's make that a capital K. And so then my net power is it's 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth times 0.97. Notice the emissivity has no units with it, times the area, which is 1.5 meters squared, times 295 Kelvin to the fourth power minus 306 Kelvin to the fourth power. Equals, am I getting that all on the screen? Just barely. Right. And what I get is about minus 99 watts. So if you're just standing outside your shower and your room is at room temperature roughly, then you're roughly radiating at like a 100-watt light bulb. And so that's a fairly significant amount of heat loss. You could ask the question, well, what if there's a fire alarm and you had to run outside, right, and it was 0 degrees Celsius outside? Well, then that would change this number to 273 from 295, and you'd have to reevaluate this thing. And I think it comes out to be about 250 watts or something like that. So it's the reason, mammals have fur to add an insulating layer so that the heat can't transfer out as easily just by radiation. It has to do some conduction and convection to get out through the fur.